Okay, so hello everyone. So today I'm going to present some of our recent works on how to see spin fractionalization in quantum spin liquid phases via Raman scattering of phonons. Okay, so this work has been done in collaboration with Shubhra from ICTS, Roderick Meisner from Max Planck, Srishti and AK Shud from ISC, and Yogesh Singh from Aiza Mohali. Okay, and these are the two references. Okay, so let me first begin with the question that what is a quantum spin liquid is the QSL basically. So historically, like these are the phases which doesn't have any long range ordering, okay, even at low temperatures. For example, if you look at this material like this praseodymium zirconate, and if you measure the susceptibility, then it shows no kind of ordering, okay, at till few millikelvin. Okay. But it turns out that this definition is not enough. In fact, you can cook up some kind of models which obeys this criteria, but you can smoothly connect it to the high temperature parabangates or phase spins. Okay. So what the understanding of the last 2 decades was that the main features of a quantum spin liquid is basically long range entanglement pattern present in its ground state. Okay. And this understanding has 2 major fallouts. One is that there is always an emergence of gauge theory in the low energy description of a spin liquid. For example, it can have emergent Z2 gauge theory or emergent electromagnetism. And another is that like the spins always get fractionalized into different kind of excitations, very exotic sometimes. Okay. So to sum up, the quantum spin liquid is basically, at least at the field theory level, it's a deconfined phase of emergent gauge theory coupled to matter fields. Okay, so the definition is good. Now comes a natural question in mind that how do you detect this statement of these fractionalizations, okay, in experimental setup? So this question has various subtleties. For example, the phase itself doesn't have any local order parameter descriptions, okay? So, and also these emergent excitations, which I'm talking about, the transforms very non-trivially under symmetry. And often they are non-local in terms of this conventional degrees of freedom. Okay? So there is a conceptual kind of question arises that what kind of probes should you even use to detect these phases? Okay? And in this regard, like it has been suggested that among the various possibilities, one can use the spin phonon coupling of the material. Okay. So what I'm going to show is basically in the spin liquid phase, due to this spin phonon coupling, the phonons coherently scatter from these emergent excitations, and therefore its frequency and line width gets renormalized. And therefore, if you study these renormalizations, you can get signatures of fractionalization. Okay. On the experimental side, this renormalization effect can be measured in the elastogram spectroscopy. Okay, so we have implemented this set of ideas in the context of 2 spin liquids. One is this Kitaev quantum spin liquid, which has a emergent Z2 gauge theory, and another is like this non-Kramers quantum spin ice, which has a emergent compact E1 gauge structure. So coming to the first example, so this Kitaev spin liquid is governed by this bond-dependent spin exchange Hamiltonian on this honeycomb motif. And the Kitaev prescribed a method to solve this. Just write the spins in terms of these Majoranas, and you get in the spectrum 2 kinds of excitations. One is this gapped but localized Ising flux, and which is basically denoted by these WPs here in the schematic figure. And another is like these gapless moving Majoranas. Okay. Note that like due to this kind of gap in this Ising flux at reasonably low temperature, these excitations are not present in your system. Okay, and that is a crucial approximations of our theory. But one can further argue that like our results, the qualitative part of our results actually is valid even if these excitations are present. Okay, so now one can get the spin phonon coupling in this kind of materials by expanding this JK in terms of the phonon coordinates delta. So basically, you are assuming that the lattice is vibrating, and that's why it's changing the coupling coefficients. So I truncate the series up to quadratic order. So it gives basically like 2 kinds of terms. One is linear in phonon, and another is quadratic in phonon. Okay. And the prescription is very simple. You rewrite all this Hamiltonian in terms of the Majorana's. Okay, so you do the transformation from spins to Majorana and you rewrite. So this in the Feynman diagram language, it translates to this kind of diagram. So H1 is like 1 phonon 2 Majorana scattering. H2 is like 2 phonon 2 Majorana kind of scattering. And then with this diagram, you calculate these renormalizations. Okay? For example, if you calculate this frequency renormalization, so the leading contribution comes from H2. And one can show that this frequency shift actually is proportional to the energy density of the Majorana systems. Okay, so if you plot it, then the profile looks like this. Okay, so it gradually saturates to some constant value. So remember, like, so to measure the frequency shift actually is like this modulus value of this. Okay. But whether it hardens or softens, that basically depends on whether the spin phonon coupling constant is really positive or negative. Okay, that is beyond our theoretical framework. So another thing is like the line width renormalization of the phonons that can be computed by H1, and if you plot it with respect to temperature, it gradually increases with decreasing temperature and saturates. Okay. So roughly, if you look at the temperature dependence, so this is like some kind of depends on fermionic distribution functions. Okay, so this if you see in the experiments really describes that there is really fractionalization going on in your spin liquids. You can do more characterization by plotting this line width with respect to the frequency, and you will see these kind of profiles, which basically follows the two particle density of states of Majorana fermions. Okay, so these modifications comes only because of these finite temperature effects. Okay, and this is in fact the measure also measured in experiments. So the material they chose is like this copper iridate, where the iridium is basically magnetic, and the Curie scale of the material is like 120 Kelvin, so which is basically this white line roughly. And so you expect like below this temperature scale, this quantum spin liquid physics sets in. Okay. And as you can see, like these are the phonon modes, different phonon modes. So its frequency and also this line width, you can see like it starts deviating from the high temperature behavior below this temperature scale. Okay, so it clearly matches with our theoretical predictions. Okay, so that was the story about the K-type spin liquid. Now let's come to this non-Kramers quantum spin-ice. So this is governed by some kind of XXZ model on a pyrophloid lattice, which is like a corner sharing tetrahedra. But you can forget all this microscopic. Just remember this thing that so there are three kind of excitations in the spectra. One is like these gapless photons. Another two are like gapped magnetic monopoles and electric charges. Okay, and all these excitations have a natural separation in their energy scales. Okay. So for this case, okay, so this kind of Hamiltonian is often realized in this kind of compounds which goes under this formula R2B2O7, where R is basically magnetic rare earth, and this can be classified into two categories: Kramers and non-Kramers. So Kramers have odd electrons in the outer shell, and non-Kramers have even electron in the outer shell. So here you particularly focus on these non-Kramers because of one funny property, that if you look at the time reversal property, due to this, it has very weird implementation in this even electron wave functions. Okay, so the spins, the transverse component Sx and Sy component of the spins is time reversal even, whereas Sz is odd. Still, it satisfies the SU2 algebra. Okay, so this immediately gives us a very nice conclusion that the phonons, which are time reversal invariant, can now linearly couple to this Sx-Sy, which was not present in the earlier case. Okay, that I showed. So, so for example, this is one such coupling. This zeta is basically the phonon modes, and Q are like some linear combinations of the spin modes. Again, you follow the same protocol, represent the spins in terms of these emergent QSL excitations, and you get this kind of Feynman diagram. So it's like phonon monopole, phonon electric charge, and phonon photon kind of scattering processes. So from these processes, you compute again the renormalizations. So the one interesting point that comes in that, for example, like if you, due to this natural separation in their energy scales, they contribute at very different energy scales. So all these excitations do renormalization at very different energy scales. Okay, so this is a schematic figure. So this might be relevant to experimentalists where like they can separate the signatures of these excitations. Again, like the similar kind of things that I showed for the earlier case, it is shown here, like the plot line width with respect to temperature. And here it shows like some monotonically increasing, which is basically some kind of bosonic distributions depends on. Okay, because the monopoles are basically the bosons here. Whereas this, if you plot it with respect to frequency, then again it follows the some kind of two particle density of states of magnetic monopoles. Okay, so that's really a generic feature. Okay, so just a few comments that this field theoretic description which have been developed here is basically very general and it's not restricted to particular materials. However, I want to make a comment that like this emergent gauge theory, which comes up in this quantum spin liquids, so it need not to be like so one basic assumption of our theory is like this fine structure constant is small, so we did all these perturbative calculations, but this emergent gauge theory need not to be reside in this weak coupling limit. In fact, from this recent numerics on some material, you can show that they showed basically this fine structure constant is tunable, and in fact in some cases like it is like 10 times than the usual QED. Okay, so that is really worrying, but one needs further experimental verification of such results. Okay, so okay, so just a take home message, like this phonon renormalization is indeed useful to characterize fractionalization in quantum spin liquid. And thank you for listening.
Thanks, Arnab, for a nice talk. We can take questions.
Not audible. Yeah. Could you go back to that slide where you showed that SX and SY were time reversal invariant, but SY was not? What precise system was that? I did not quite understand.
Sorry.
So we know that momentum is time reversal non-invariant, right? Momentum will change sign, but these are spins, I assume.
Yeah. So these are basically some kind of spins which you get like effective spins. So basically, what happens is like if you look at these non-Kramers, this for example some material if you choose, then at the ground state level it has a doublet structure. Okay, so the ground state is like twofold degenerate. Now if you project all your angular momentum operators, for example Jx, Jy, Zz, you get these effective spins, but these spins have a very weird time reversal property. For example, like this spin up and spin down state has a very like under time reversal, like one goes to minus of another thing, like plus if you take it goes to minus of minus, like but here these two doublet actually just goes to like plus goes to minus. This kind of structure is there. So
but that is still not time reversal invariance, right? If plus goes to minus.
So that is the state level statement I am saying. But if you construct from that state like Pauli X matrix, so Pauli X matrix it's like plus plus minus plus minus plus, right? So it basically changes to itself. So
Okay.
Yeah, thanks, Arnab. Thanks for the talk.